We'll start in 1 minute. We'll continue with the final exam review today. So Wednesday, December 2nd, from 7:30 a.m. to 9:30 a.m. is when the final will be on Zoom. And today is the last day to do the student evaluations on Moodle. So if you haven't done those, try to get those done today sometime.
Question, do you happen to know when those close? If it's at a particular time today, or is it just like sometime today?
Usually it's at midnight.
Okay, cool. Didn't know if it was like it closes at 3 o'clock, so make sure you do it before then, kind of thing.
Yeah.
Thank you.
If you can't access it, it means it's closed, probably.
Okay.
So.
Thank you.
Okay, let's review hydrostatic force. So remember, the hydrostatic force is rho times G times A times D. So A times D is the volume. It's the area times the depth. Rho is the density of the fluid. And G is the gravitational acceleration constant. So if the volume is measured in cubic feet, which is what this example is going to have. So if volume equals A times D is in cubic feet, then rho times G is the weight density of water, which is 62.5 pounds per cubic foot. Okay, so in this particular problem, it says an 8 feet by 6 feet rectangular vertical plate is submerged in water with one long side at the water surface. Find the hydrostatic force against one side of the plate. Okay, so the surface of the water And the long side, 8 feet, one of the long sides is at the surface. So if we assign x to be 0 feet below the surface, and then x equals 6 is the bottom depth. And then if we construct a rectangle with width delta x at depth x sub I, then we can write down the hydrostatic force on that rectangle, or approximate it. So F sub I represents the hydrostatic force on the ith rectangle, which will be approximately 62.5 pounds per cubic foot times the volume. Okay, so the area of the rectangle is 8 times delta x, and the depth is x sub I. Okay, so 8 times, we can simplify a little bit. 8 times 62.5 is just 500. And then rearrange delta x and x sub I. So 500 times the depth x sub I times delta x, which is the width of that rectangle. The force, the hydrostatic force on one side of the entire vertical plate is approximated by adding up all of those hydrostatic forces of the n rectangles. So from I equals 1 to n of 500 times x sub I times delta x. This is a Riemann sum, so if you allow n to go to infinity, then this is just the definite integral from x equals 0 feet to x equals 6 feet of 500 times x dx. So we might as well go ahead and evaluate this. So 500 times x to the second over 2 from 0 to 6, or 250 times 36 pounds. So this is just 9,000 pounds. That's the hydrostatic force on one side of the plate. Okay, then moments and centers of mass. So these are the formulas for that. Let R be the region in the xy plane with uniform density rho between the graph of y equals f of x, the x-axis, and vertical lines x equals a and x equals b. The moment of the region R about the y-axis is m sub y equals rho times the definite integral of x times f of x dx from a to b. The moment of the region R about the x-axis is m sub x equals rho times the definite integral of 1/2 times f of x squared from x equals a to b. And then the mass of that region is just the density times the area. So it's rho times the definite integral of f of x dx from a to b. Okay, and then the location of the centroid, or the center of gravity, or the center of mass, is the ordered pair x bar, y bar. X bar is the moment of the region about the y-axis, m sub y, divided by the mass m, and the y-coordinate of the centroid is the moment of the region r about the x-axis, divided by the mass. Okay, so let's do an example. Find the location of the centroid of the region bounded by f of x equals x squared and y equals 0 for x values from 0 to 1. Okay, so the moment of that region about the y-axis is just rho times the definite integral of x times f of x. So x times x squared is x to the third, and then from 0 to 1. So this one is rho times x to the fourth over 4 from 0 to 1. And then we can write this as 1/4 times rho.
So why is it x cubed?
I multiplied x squared times x. Okay, then the moment of r about the x-axis, m sub x, this is rho times the definite integral of 1/2 times, I'll go ahead and write it, 1/2 times f of x squared dx from x equals 0 to 1. And then x to the second is x to the fourth times 1/2, so that's x to the fourth over 2 dx. And so we get rho times x to the fifth over 10, evaluated between 0 and 1. So this becomes 1/10 times rho. And then the mass of that region is rho times the area. The area is the definite integral of f of x from 0 to 1, or rho times the definite integral of x squared from 0 to 1. So we get rho times x to the third over 3 from 0 to 1. And we just get 1/3 times rho. Okay, then the centroid, x bar, the x coordinate of the centroid, this is m sub y divided by the mass. So it's 1/4 rho divided by 1/3 rho. The rows cancel, and 1/4 divided by 1/3 is just 3/4. And y bar, the y coordinate of the centroid, this is m sub x divided by m, so 1/10 rho, 1/10 times rho divided by the mass, 1/3 rho. The rows cancel, 1/10 divided by 1/3 simplifies to 3/10. So maybe we can sketch a little graph just to see if this is believable. So it's the region below the graph of f of x equals x squared from 0 to 1. So that's a rough sketch of f of x equals x squared. Okay, so the centroid is x bar y bar equals 3/4 for the x bar and 3/10 for the y bar. So 3/4 for x is about here, and 3/10 right in there. So it's conceivable that that's where the centroid is. Okay, the next page. So chapter 9 material. We only covered a couple of sections in chapter 9. So two different kinds of differential equations to solve. A separable equation is a first order differential equation that can be written in the form the derivative of y with respect to x equals g of x times f of y. So a hint on remembering how to solve a separable equation is if you can get on one side a function of y times a function of y times dy, and that's equal to the other side, which is a function of x times dx, then you integrate both sides. So the idea is you separate the variables and then integrate after that. Okay, so for this one, solve the differential equation dy dx equals the quantity y plus 1 times the quantity 2x plus sine of x, where the y values are greater than -1. And the initial condition, y of 0 equals 2 plus e to the 5th. So in other words, when x is 0, the y coordinate will be 2 plus e to the 5th. Okay, so the first thing we do, we can write down the separation. So on the left-hand side, well, we're going to divide both sides by y plus 1, and then multiply both sides by dx. So when we do that, we get dy over y plus 1 on the left-hand side. And on the right-hand side, we have the quantity 2x plus sine of x dx. And then we integrate both sides. So integrate the left-hand side with respect to y. Integrate the right-hand side with respect to x. Okay, so an antiderivative of 1 over y plus 1 is the natural log of y plus 1. So we don't need the absolute values because we have this condition, y is greater than -1. And then on the right-hand side, an antiderivative of 2x plus sine of x is x to the second minus cosine of x, and then plus a constant. So you might remember that some differential equations couldn't be solved explicitly for y. And so in some of those, we just left the equation without having an explicit equation for y. But we can solve this equation for y. So the natural log of y plus 1 equals a function of x. So that means the argument y plus 1 is equal to e to that function of x. So e to the x squared minus cosine of x plus c. Right?
Yeah.
We're all in agreement? Okay, then subtract 1 from both sides. So y is equal to e to the x squared minus cosine of x plus c minus 1. And now what we want to do is determine what the constant of integration is based upon the initial condition. So y of 0 equals 2 plus e to the 5th. Okay, so in other words, when x equals 0, the left-hand side y will be 2 plus e to the 5th. And then on the right-hand side, we replace every x with 0. So we have e to the 0 minus 1 plus c, because cosine of 0 is 1. So we have e to the negative 1 plus c, but I'm going to write negative 1 plus c as c minus 1, just for convenience. And now we want to solve this for c, this equation for c. So first we'll add 1 to both sides, and we'll get 3 plus e to the 5th equals e to the c minus 1. C is in the exponent, so, and we want to solve for c, so we'll take the natural log of both sides, and we get the natural log of 3 plus e to the 5th equals c minus 1. And finally, c is equal to the natural log of 3 plus e to the 5th plus 1. Sort of seems goofy, but who knows what could happen. So anyway, our function y will replace c with the natural log of 3 plus e to the 5th plus 1. So y is equal to e to the x squared x squared minus cosine of x plus the natural log of 3 plus e to the 5th plus 1 minus 1. So all of this is in the exponent.
Not a very pretty equation, but it works.
What's that?
It's not a very pretty equation,
Yeah.
but it works.
Yeah, sometimes you just settle for what you can get. All right, the next one, linear differential equations. This one is just a first order. Hey, a first order meaning first derivative. A first order linear differential equation can be written in the form the derivative of y with respect to x plus p of x times y equals q of x. So if you have a first order linear differential equation that's not in this form, then the first step to solving it is to get it into this form so that we can find what is called the integrating factor. So the integrating factor it's referred to as capital I of x. And when it's in this form, the integrating factor is e to the indefinite integral of p of x dx. And then when you find the integrating factor, you multiply both sides of this equation by the integrating factor. The result is the left-hand side will be the derivative, the first derivative of a function, and so on. Okay, so here's a first-order linear differential equation that's in the form that we want it. The p of x is 1 over x. So the integrating factor is e to the indefinite integral of 1 over x dx. So this will be e to the natural log of x, which simplifies to x. Okay, and x is greater than 0, so we didn't need an absolute value. Okay, then we multiply both sides of this equation by x. So we have x times the quantity dy dx plus 1 over xy, and then x times 1 over x squared. Okay, so x times the derivative of y with respect to x plus y equals 1 over x. Okay, the left-hand side is the derivative of a function involving the product rule. So we'll rewrite the left-hand side as the derivative with respect to x of x times y equals 1 over x. And if you're in doubt, you can verify that the derivative of x times y with respect to x. Remember, y is just a function of x, so use the product rule to find the derivative and you'll get this expression. Okay, the goal is to solve for y. So now we integrate both sides. So the left-hand side is the derivative of x times y with respect to x. So when we integrate that, we just get x times y. And then we integrate the right-hand side and we get the natural log of x plus a constant. And then divide both sides by x. So we get y equals the natural log of x plus c, all divided by x. And then the initial condition, when x is 1, y is 5. Okay, so when x is 1, y is equal to the natural log of 1 plus c over 1 equals, we can go ahead and simplify this. The natural log of 1 is 0, and c divided by 1 is c, and so this is equal to 5. That's the initial condition, and so our function y is equal to the natural log of x plus 5, all divided by x. Okay, those are the two types of differential equations to know for the final. Okay, then some material from chapter 10. Okay, the following 4 examples use the same parametric curve defined by x equals t plus 2 and y equals t to the second minus 2t for values of t between -1 and 3. Okay, so in the first one, eliminate the parameter to find a Cartesian equation for the curve. So it looks like the easiest thing to do is solve this equation, x equals t plus 2, solve for t. So t is equal to x minus 2. And then in the other equation, replace t with x minus 2. So we get y equals x minus 2 squared minus 2 times x minus 2. And then algebra and arithmetic. So x minus 2 quantity squared is x squared minus 4x plus 4 minus 2x plus 4. And so the Cartesian equation that we get is y equals x squared minus 6x plus 8. Okay, the graph of that is a parabola. So I didn't mention anything about it in this particular problem, but review how to graph a curve that's given in parametric equations. We can do a couple of points. So our t-values range from -1 to 3, and then after picking the t-values, we find the corresponding x and y values. So let's just try -1, 0. Well, why not all of them? 1, 2, and 3. Shouldn't take too long. Okay, so when t is -1, the x-coordinate, -1 plus 2 is 1. And the y-coordinate, -1 squared is 1, minus -2 is 3, so 1, 3. When t is 0, the x-coordinate is 2, the y-coordinate is 0. When x is 1, the x-coordinate is 3, and the y-coordinate 1 squared minus 2 times 1 is -1. When t is 2, the x-coordinate is 4, and the y-coordinate is 0. And then finally, when t is 3, the x-coordinate is 5, and the y-coordinate is 3. So let's see if we graph that. Shouldn't be too hard to graph. X ranges from 1 to 5. So when t is -1, the first point is 1, 3. Then 2, 0, 3, -1, 4, 0, and 5, 3. Yeah, and then remember that the arrows that indicate the direction of the parameters. So we would have arrows in that direction if we were to graph that. Okay, the next part, find an equation of the tangent line corresponding to t equals 2. So in order to find an equation for a tangent line, we need to know what the slope of that line is and what a point on that line is. So to find the slope of a tangent line, we need the derivative. So we need to know what dy dx is. And when x and y are given as parameters or parametric equations in the variable t, dy dx is dy dt divided by dx dt. Okay, so in the numerator, dy dy dt. So y is t squared minus 2t, so dy dt is 2t minus 2. And in the denominator, the derivative of x with respect to t is just 1. And then at t equals 2, the slope of the tangent line is 2 times 2 minus 2 divided by 1, or 2. Right? That's the slope of the tangent line that we're looking for. And we also need a point. So the x and y coordinates of the point corresponding to t equals 2. This is when t equals 2. Okay, the x coordinate when t is 2 is 4. And y is 0. Okay, so now we have all the information we want, or we need. So we can write y minus 0 equals 2 times x minus 4, or y equals 2x minus 8. That is the equation of the tangent line. So we can look at our graph and see if that is believable. So this point right here is 4, 0. And I suppose it's conceivable that the slope of that line that passes through that point is 2. At least it's positive. And then the y-intercept is negative 8. Okay, the next part, find the area below the curve and above the x-axis for values of t from 2 to 3. Okay, so a reminder about the area below a parametric curve. Okay, so if the parametric curve for x is lowercase f of t and y is lowercase g of t, and if we were to define this Cartesian equation as capital F of x, so just think of this as capital F of x, the Cartesian equation. Then the area below capital F of x from A to B, we're familiar with that, right? The area that's below F of x from A to B. And then in terms of the Cartesian equation, well, we change from x values to t values. We'll refer to those as going from alpha to beta. And then the integrand is g of t times f prime of t dt. Okay, so the idea for this original function, capital F of x, y equals capital F of x. But parametrically, y is equal to g of t. So f of x corresponds to g of t. And since x is f of t, dx is f prime of t dt. So anyway, this is our formula for finding the area. G of t, so in our problem, g of t is t to the second minus 2t, and f of t is t plus 2. And our t values are from 2 to 3. So the area that we're looking for, the definite integral from t equals 2 to 3 of g of t, t to the second minus 2t, times f prime of t, which is just 1, dt. So that's a pretty simple integral to evaluate. So we get t to the third over 3 minus t squared, evaluated between 2 and 3. So let's take it a step or two further. When t is 3, 3 to the third over 3, 27 over 3 is 9, minus 3 squared is 9 minus 9, and then minus the quantity 2 to the third over 3 is 8 thirds minus 4, which is minus 12 thirds. And so we get the negative of negative 4 thirds, which is positive 4 thirds. Okay, the next one, set up an integral for the length of the curve on the interval from t equals -1 to t equals 3. Okay. So a few weeks ago, we learned that the arc length of a parametric curve, here's the formula for it, the definite integral from alpha to beta, and the integrand is the square root of dx dt squared plus dy dt squared dt. So we're just going to set this one up. So dx is, or I should say x is t plus 2. So for our problem, dx dt is just 1. And y is t squared minus 2t, so dy dt is 2t minus 2. And then the t values range from -1 to 3. So the definite integral from -1 to 3, and the square root of 1 squared plus the quantity 2t minus 2 squared dt. You can take it further if you want, but this is a pretty good answer for setting up the integral. Hey, the next page. This time for a polar curve. We'll graph the polar curve, r equals sine of 2 theta. We'll find the area of one loop, and then we'll set up an integral for the arc length of one loop. So generally what I do is I graph the Cartesian function and then convert that by looking into a polar curve. So r equals sine of 2 theta. So I start out by writing 0 less than or equal to 2 theta is less than or equal to 2 pi. If I solve for theta, divide all 3 parts by 2, I get 0 less than or equal to theta less than or equal to pi. This tells me what one period of that particular sine function is between 0 and pi. So Cartesian graph first, but we're going to go all the way from 0 to 2 pi. Subdivide each of those. So this is pi over 4, pi over 2. 3 pi over 4 pi, then 5 pi over 4, 3 pi over 2, 7 pi over 4. And then the sine curve for sine of 2 theta. We have 2 periods here. Okay, then the polar curve. So these dashed lines are where the multiples of pi over 4 are. Okay, so the polar curve, the r value, yeah, this is the r value and theta value. So when theta is 0, r is 0. And by the time we get to pi over 4, the length of r is 1. So we get to this point, the loop, first half of the first loop. And then from pi over 4 to pi over 2, we go back to 0. Between pi over 2 and 3 pi over 4, the r values are negative, so they're on the opposite side of the origin. So we go down to this point, a length of 1 from the origin. And then from 3 pi over 4 to pi, we're still negative, but we go back to 0. Then from pi to 5 pi over 4, we're positive again. So we're going to get to here when we're at did I do that right? Let's see. From, 3 pi over 4 to, suddenly I'm confused.
I think it might be in like the next section down in quadrant 3, third loop.
So
If we got
maybe if I
pi-
retrace. And then pi over 2 to 3 pi over 4.
And then we go down into quadrant 4, but when it comes back,
Oh.
it reaches out, we go into quadrant 3.
Yeah, this should be down here, right? And then
Right.
back to 3 pi over 2, we're back at 0. And then from 3 pi over 2 to 7 pi over 4, the r values are negative, so we're up here again. And then back to 0. Yep.
Yeah.
Okay, so that's the graph of the polar curve. So find the area of one loop. So if we use the first loop, we're going to go from 0 to pi over 2. And so the area of one loop so from 0 to pi over 2, it's, the formula is 1/2 r squared d theta. So 1/2 times sine of 2 theta squared d theta. Okay, so when we square that, sine of 2 theta squared, we use that particular identity for sine of 2 theta squared. So we're going to get a definite integral of 1/2 times 1/2 minus cosine of 4 theta d theta. Yeah, it messed up again. So we need cosine of 4 theta over 2 also. So if we just factor out the 1/4, we're going to get 1/4 times the definite integral from 0 to pi over 2 of 1 minus cosine of 4 theta. And finally, 1/4 times 0. I don't know what's wrong with me. Theta, the integral of 1 with respect to theta is theta, and then minus 1/4 sine of 4 theta. Evaluating this from 0 to pi over 2. So when we evaluate this, there's only going to be one term that's non-zero. That's when theta is pi over 2. So this is 1/4 times pi over 2, which is pi over 8. Okay, so that's the area of one loop. And then set up an integral for the arc length. So the arc length formula is the definite integral from alpha to beta, and it's the square root of r squared plus dr d theta squared d theta. Okay, so r is sine of 2 theta, and dr d theta is 2 times cosine of 2 theta. So when we square those, and then our integral will be from 0 to pi over 2, and then the square root of sine of 2 theta squared. And then when we square the derivative, we get plus 4 times cosine of 2 theta squared. Okay, so that's the setup. Okay, and we're out of time, so keep reviewing as much as you can, and then we'll have the final 1 week from tomorrow.